let me start with, I want to recall something from last time because I want to count a little bit before we go to the next. Counting is half of the job, basically, so. So I wrote down last time, and I hope it went through, that when I draw this, let's maybe already draw an example. I was drawing this Hanani-Witten setup where these were the D4 and these were the NS5 brains. So the positions of these external brains, we said that they correspond to the mass parameters. The distance between the two different internal ones will be the Coulomb moduli, and the distance between the two NS5s would correspond to the coupling constant. And if you want to make something more general, the idea is that the number of faces in your diagram, it will give you the dimension of the Coulomb branch. And let's immediately make two more examples here. So this is another example that is of interest, and this corresponds to SU3 with 6 flavors. And here you see we have 2 faces, so this is the correct dimension of the moduli space. And also the number of external brains, -3. 3 is because we can shift this way, and also there is one more because everything should hold together, so there is a condition that everything is conserved. So this is the total number of parameters of the theory. So these are the ones that really appear in the Lagrangian. And they can be masses and coupling constants. And here we can also make a very quick counting. So there are 6 masses, which will be these ones. And here there is 1, 2, 3, 4, -3, 1 coupling constant, which is the coupling constant of this SU3 color group. But let me make another example, because there are also quiver theories. So let's study this example. This is an SU2 cross SU2 theory with a doublet here of fundamental and another one here. So what happens? Here we have 4 masses that will correspond to the D4's external. Here we will have 2 faces that they will give you the Coulomb branch. And here we have 1, 2, 3, 4, 5, 6, -3 is 3. So there are here 2 coupling constants, Q1 and Q2. And what are we missing? We are missing the mass of the bifundamental. So let me actually write here a little bit nicer. So let me denote in this way. So in parentheses, I say that this is of the first color group, and this is A1 and A2. This is a little bit over counting, but I needed to define the...
You're writing it as a U2.
Exactly, I'm writing it as a U2. And because you see, I cannot decouple, so the U1 that I am decoupling here is because I have one color group and it's easy. But here there is a relative U1 that I cannot decouple. And this will become the mass of the bifundamental. So it will be the sum of the masses from the one color group, and I am writing it here a little bit more general so that it's for any, minus the other ones that are next to it. So this is always the mass of the bifundamental.
So the plus sign there would correspond to the overall U1.
The plus sign will be the overall one that I am allowed to decouple by shifting my V. So that's how the counting works. And of course, this is extremely important because then all of these parameters will appear in the... And here, let me be very explicit. So here there will be a U3 that will come from the trace phi to the third and from a U2 that will come from the trace phi squared. And these will be the two parameters that will appear in my Seiberg-Witten curve. And here there will be two, let's call it U1, 2, and the same thing, let me put 1, 2 for the two different. So these are the parameters that will appear in my Seiberg-Witten curve. Are we happy with this? So this is sum again over all the branes, A2, yes, this is a 2. So from the second color group. Good. Okay, I will go back immediately to the curves, but before I go, let me tell like really quick Seiberg-Witten theory. Okay, the first very important thing, so I already started using superspace last time. Let me introduce a tiny little bit more of it. Very tiny little bit. So, when I write this, I mean that I have to integrate over the holomorphic, but the anti-holomorphic part of the thetas. And so I am writing down, let's write for pure n equal to 2 Yang-Mills, the Lagrangian. So phi capital now is my chiral, my n equal to 1 chiral superfield. So this is the one that will give the d terms eventually. Okay, and there is a trace here. So this is how the Lagrangian of pure n equal to 2 Yang-Mills looks like. And one thing that is very nice is that when you have n equal to 2 supersymmetry, you can introduce a second theta, and in fact, put them together in a doublet in this way. So you have the theta that you had before in the n equal to 2 superspace, and one more. And by using this, you can define a new chiral superfield, let's call it psi, that starts with n equal to 1 chiral superfield. It has the n equal to 1 vector superfield, and of course some auxiliary stuff. And if you want in components, you can also write it like this. Theta I, lambda I, and then you can continue. Here is also very important to do your indices right, because you see the fermions, they are Grassmann. So if I contract in my things, this I have to make symmetric. So I get this type of term. So this is the F mu nu, the Ceph dual part, and this is the triplet of the auxiliary fields. So I don't know if this is fast, but this is all the truth. And the moment you do this, you realize that you can write this action as one single now. Okay, this is really misuse of, or maybe I will not misuse the notation, I will do it nicely. So this action, you can write it in this form, and we observe that this gadget is holomorphic. Now, in general, if we want to study, because this is what we want to do when we do the Seiberg-Witten theory, if we want to study the effective theory in the IR, what happens is that, of course, you can create new terms in your superpotential, but there will always be, so the effective action will always have a holomorphic part that we will call prepotential, and it will be some function of this superfield psi. And there can also be, in principle, and now let me write 8, which is all the thetas and all the theta tildes, and I integrate also over the bars of that. So there can be a non-holomorphic object that you can write down. But very quickly, if you count, you see that this object will be irrelevant operators. So in the IR, this goes away. And that's all we have to work with.
Sorry, but
Yes, please, yes.
Sorry, just before asking the question, let me ask you just a question. So that action, this in order to specify how we get the Kähler potential, I mean, where is the weak or
So the Kähler potential is here, and it will appear by projecting this guy.
super covariant.
Yes.
Is also against the okay. Also, this argument about ignoring this term with the IR, I mean, isn't cyberbit theory an effective theory?
Yes, it's an effective theory in the IR. So we really drop all of the terms. If you wish, if you keep K, the momentum, all the terms that will come with K positive powers, you have to drop them. So all of this stuff, you have to drop.
And derivative expansion.
Yes.
Not
Yes,
not
yes.
Lilienthal derivative.
Think that you do a derivative expansion. So here, for example, there will be operators with more than 2 derivatives.
But what I'm saying is that F, this prepotential.
Yes. So this is
also
good.
That also could be,
Here there is only one derivative.
Yeah, but dimension-wise it could be complicated.
It could become complicated, but they all have to come from the same thing here, and there will be no higher derivatives. But here they will have to be higher derivatives no matter what you do. And together with supersymmetrizing everything, you will have to drop everything.
Psi has dimension 2, right?
Yes. So it has the same dimension as phi.
Theta has, d theta has dimension -4.
I mean, it's not only dimensional analysis, right? Because it's what he said. Here, for example, maybe you can write psi to phi, to some power. That's also irrelevant.
But at least the leading term, I want to see how many derivatives is that.
Yes,
Yeah,
so,
this takes H to be psi bar.
yes.
What is that term?
So that's not good enough, right? Because you have to act with 8 of these guys. So this is dimension 4. So you will basically create 4 derivatives. So for example, you will have something like d to the 4 phi bar acting in different ways, the derivatives of this. So that's precisely what I said. You need to drop it. And because of supersymmetry, of course, you will need to drop everything that is its supersymmetric friend. Good. So so this is the first statement, that we have only this gadget and nothing else. And now we go to the Coulomb branch. We turn on all the A's. What we do is we break SUN down to the Cartans. And the statement, let me first write the statement. The statement is that all the information you need to recover this function and let me now write like this, because we really went and we set all the phi's. So it will be a function of the A's, is encoded in a curve. And when Seiberg and Witter discovered it, it didn't have. What we started doing last time with the M5 brains, we found a way to materialize the curve. But back then it was just an auxiliary thing, an auxiliary game. And so there is a curve, and I am writing here basically what I was writing last time. And in order to do something with this, so now I'm just doing the statement, you need to also know a meromorphic form that, as in 1 second we will see. We will write it like this. And the D, it's the D of something, which we will call the Seiberg-Witten curve. And if you know these things, you win. You can do everything.
Can I ask?
Yes, please ask.
Something which is others doing, but it also is addressing.
Yes. No, it's okay. We can turn off the recording.
This Seiberg-Witten effective theory, it's supposed to be theory of some U1 gauge fields.
Yes.
That are unbroken like that, coupled to some dions, right?
good, but the dions you don't write in. I mean,
Don't
the
write the
yeah,
reaction,
yes,
But there is some action, low energy action of the
yes.
abelian fields with some prepotential like that. But now let's say I integrate out the dions. Is this the integrated out action?
So yes, this
Or
is
is it-
really in the IR. This is below everything. So this action, so when you do your renormalization, you set mu to A. So let me write 1 second. So good, very good. So there will be some type of curve. Let me for now write a stupid torus that has the usual A cycles and B cycles. So let's really write. I will write the mass of the dions. And the moment you have these things, first of all, you can compute. Okay, this is statement number 1. Basically, you can compute the prepotential from this formula. And here is the mass of the dions. By the way, this is also the central charge because they have to be BPS, so we go to the supersymmetry algebra and we set the mass equal to the central charge. Okay, good. So this is the formula. So this has mass at least A, or this is a scale, right? So, and this is the scale that we have when we do our RG. So these gadgets will not be in this Lagrangian. We will recover them doing this game. Okay, good. Now, this has a very nice geometric interpretation in the way I was trying to explain last time.
No, so sorry.
Yes.
So what I meant was that if I take this Lagrangian,
Yes.
Lagrangian,
Yes.
Lagrangian, okay,
The UV.
the UV Lagrangian.
Okay.
Yes,
So that's not that.
it's not that, yes. And then I give this Coulomb branch wire. And then in the Lagrangian I read off the massive particles.
Yes.
These are going to be the W bosons to get mass.
Yes, very good.
And you can think of this action as being obtained by integrating out the W bosons.
Yes.
Not the magnetic monopoles.
I mean, okay, we have to be careful,
Stuff
right?
like that.
We have
So
to be.
is that
We have to be careful because this you really have to do formally at the level of the path integral, right? And at the level of, nobody knows how to do this, I think. But formally at the level of the path integral, what you need to do is you would need to have all the subtle points, so not only all of them, and really with all of these terms integrate out.
Also, so these dions and monopoles are infinity heavy, right? Where this
Yes.
SU and the in terms of W bosons is weakly coupled. So where we can do that calculation goes to an
But I
But
remember
in
Mark
Mark Ormofil, we can just push it in as far as we can. Then we hit singularities, then we do a discussion.
No, no, I just remember that Martin was doing something, some extra integrating out on top of this Cyber-Witten effective action.
Okay, so there is one other thing that this is what you have seen. So you can maybe start, let's say, with the conformal theory, or asymptotically conformal, they call it, that you turn on masses to all of the gadgets. So, but again, this will be some curve. It will just also be a function of the masses, the way we did, for example, last time. And you can start sending these masses to go to infinity, and then you can precisely do it how to integrate out. You impose matching conditions, and then you can write the curve without these specific masses. So this is what is written in all of these old papers. You can do the conformal case first, and then you can start kicking out hypermultiplets in this way. So maybe this is what you remember. Maybe not, I don't know, yes. So, no. So, and now this, what is very nice is that it has a very nice interpretation with the, and maybe let me, Okay, remember that I have this. Now I will tell you how to derive this in a very easy way. So what you do is that in M theory, you also have M2 branes. So these are the only extra objects that we have. So if we want to describe these guys, that's what we need to use. And in order to describe, so these are point particles on the, so there is some, where the gauge theory lives. So these will, so the M2 will have, an R1 here. And there is, what is left is something that is two-dimensional. Let me call it D, some type of disk. So this object will be, if you remember this type of shapes that we had, okay, I don't draw the three-dimensional or whatever, I draw this very stupid little picture. So these M2 branes, they can end on this is the M5 brane. They can end on this, and so this disk will end here on some contour. And what do I need to do if I want to calculate the mass of a particle that comes from an M2 brane? I need to do the world volume integral of some two form. But remember, what did we have? Right? We had V and T. These were the coordinates we had. And in fact, T were e to the s. So I need to do this integral on D. We did it, basically. So we will have, okay, up to signs, I'm not keeping track of anything. So we will have the dV, right? And now I can write the ds like this. And of course, then I can write that I have to do an integral over the curve. I can pull out the v dt divided by t. And this is what we call the Seiberg-Witten curve. Differential, sorry. So this is what it is. Good? Okay, let me write nicer. Let me stop deriving everything by myself and let me copy. So this is what I'm doing, log. So now in this setup that we have a way to find the curve, and we have a way to find this in the same coordinates, and now we can calculate everything. And maybe, okay, maybe I can say one word. Why on earth, trying to solve this IR problem, you got a curve? So first of all, people already, Seiberg, from his n equal to 1 things, he told us that the tau IR is, okay, tree level might be there. There is a log term from the one loop calculation, and then there can only be instantons because of holomorphicity and nothing else. So basically the same thing will go to the F. Then you start looking of how things move around. So you have this U, so you look on this plane how things work. You discover that there's a monodromy, so there should be other singular points. Then you say what should be the symmetries of my Coulomb branch. You remember that there was a U1, but because of instanton and because the one loop is broken to some discrete subgroup, you use this discrete subgroup, for example, for SU2, the symmetry is sending U to minus U. So all the singularities should be organized on this. So you use your symmetry in this way. You find how they should be organized. And then you say, what is the minimal thing I could do? One minimal thing is that I can have at infinity, at tree level or whatever, perturbatively, one singularity, which I know. And then there will be another one maybe at 0. You prove that this is wrong. Then you continue. Let's say that it's 3. You say, what would be the 3 ones? And then here comes the magic of Seiberg and Witten. They say, well, Another singularity I can create if a monopole becomes massless. You study what happens around the monopole, you match the monodromies, and you find the curve. And then, of course, later people studied more carefully and they showed that there should be no other singularities. So this was how you use only holomorphicity and symmetry to really derive the fact that there should be a curve there. Okay, this is very quick, of course, if you have not seen this, but good. So should we go back to our curves now? Yes, please. No, no, please, please.
So we start off, we had like a tau UV,
Yes,
and for homologous, we can define an elliptic norm, which is like e to the 2pi tau UV.
yes,
And then from Cyberg, we know that there's tau IR, which has like a tau UV, and then there's a log correction, and then there's some series of
yes,
countercorrection. Now, if I try to think of this as a complex structure modulus, and I associate it to a torus, just say for the SU,
yes, very good, yes.
then the complex structure modulus is changing.
So very good. So actually, this is something that Seiberg and Witten got wrong in the papers originally, and it was fixed only by Gaiotto, Aldeide, and Tachikawa in the AGT paper. So at the beginning, and they said that the tau UV should be equal to the tau IR, Seiberg and Witten. That was wrong. And then you can use this formula, and you can calculate tau IR as a function of tau UV. And it's not equal, it's a function, and that is highly non-trivial with theta functions. So it's,
Right.
yes.
But I'm asking from the point of view of just describing a torus. What does it mean to have a different complex structure modulus?
At the UV,
I mean,
very good,
So
very
the UV tau is the more parameter of the Gaiotto.
yes. So let's do a little bit more Gaiotto, because as you will see, the Seiberg-Witten curve describes this non-trivial topology things, whereas the Gaiotto curve is something that lives on a sphere. So there is a difference between the two things. So let's do a little bit more.
So they're just different curves.
Yes. I mean, in some sense, the one is a rewriting of the other, but the interpretation we give to things make these things to be different.
So tau UV, let's say assuming with overload, which is this is what the formula.
It's a position of a. So it's coming, yes.
Now this is torus.
No.
Sphere with 4 while tau IR is a torus. In this then torus.
Right. But especially if you can think of it as complex structure of
Yeah, complex structure of a sphere with 4 punctures.
So not of a torus, but so you fix the three positions of the four punctures, and there is one left and this position. But you will see, I will.
4 it's equal, right?
Yes, in n equal to 4 it's equal. Because the n equal to 4 curve is a torus and there is nothing else in life. But everything will, this is what I'm going to do basically. So let's write again. Okay, so I will derive everything explicitly for you, for SU2 for flavor. And then I will ask you to use a tiny little bit your imagination for the rest. I mean, it will be obvious. So, yes.
We will ask the question later. Make the comment later. But because the language is this the statement, namely, one would think that if it's a superconformal theory, then the tau will not change as you slow down.
But
Right,
it really seriously changes, right?
Because of non-perturbative
Yes,
corrections.
it really, yes.
Is that how?
I think the point is that the moment you leave, so the RG flow is absolutely not conformal. It's a mess. The only thing that it does is that it preserves n equal to 2 supersymmetry. So,
Also, I mean, like, you go to the Coulomb branch, right? You
yes.
compose material. So also branching of beta function is a possibility. I mean, it's exactly marginal to all loops, but at a superconformal point. As soon as nodes move around, you will not.
Okay, so this is what we derived last time, right? I mean, everything I will do everything extremely explicitly, I think. I mean, you can complain.
Yes.
So we got this by looking at the asymptotics, right? Now, first thing we want to observe is let's try to solve for V. What you get is the following. Maybe I need to write also. So when I started solving for the asymptotics last time, I wrote the curve in this form.
By the way, can you also do a quick example of starting from the curve and actually getting the free potential? That's too much.
I could do it next time if you want, because so it's a little bit non-trivial calculation because you have to have these hypergeometric functions, and I don't want to try to do it now for fun, because I will, for sure, I will fuck it up a little bit. The answer is always, actually, the answer, very roughly, up to all mistakes, is very easy. The Seiberg-Witten curve always has a structure square root of something, so it really immediately looks like. Basically the integral definition of a hypergeometric function. And the only thing that is, you have to do right is you have to say which precise ABC is in the, so that's the job. But that I will not get it right if I try to do it now. So. But for SU2 for flavor, I can definitely do it. This is not a problem. For higher rank, it's a huge pain. So, I didn't do anything. I took this way of writing the curve, and I brought it in this form. In this form, we already start seeing things, and the first thing we see is that we have two seats. So let's call the V plus and the V minus. Here, this is M capital, and M capital is the sum of all the masses. It always appears like this there. In some sense, it completely makes sense that it's there because it really has to do with the center of mass of the whole thing. Good. So I see two seats, two solutions. Because of this is a, t to the 4 type polynomial. So it has 4 solutions. So here there are 2 cuts. Of course, the precise way you draw the cuts, it's a little bit on you. And another thing that I see, and in fact, to really see the way Gayotto wants you to see it, you really need to do a slight change of variables. So you need to say that V is xt, and then you have x plus minus, and then there will be, the same type of way. But here there will be a t minus 1, t minus q. So this we saw already here, and here we see that it has poles at t equal to 0, 1, q, and of course if you set t to go to 1 over v, you see that there is another pole at t equal to infinity. So t equal to 0, 1, q, infinity. There are poles, and we can put them also here. There will be the image of them in both of the seats. So this is the structure. In fact, there is one more thing that Gayotto said that is very nice. There is another, let me just write it. For now, I will not tell you what it does, but we will see it in a moment happening. There is a good rescaling that you can do before doing this renaming. This basically really makes, and then you do this. This really will make the punctures the way we know and love them, but it will come. So this is a structure. All the magic is in this shift. So you have to be a genius to do it, but he did it. Yes. So now, and let me even say, in general, if you do all of these shifts and all of these cooking up things, you rewrite your curve in the following way. You rewrite your curve in x squared is equal to something which is a function of t. So that's what is called the Gayotto curve. That's the form. And what is amazing in this form is that there is no cut to be seen anymore. There is this beautiful meromorphic function, because I have done all of this thing, and there is the square here. I have this function that only has poles. So the way he interpreted this writing is that all I have in life is a sphere with 4 punctures on this 0, 1, q, and infinity.
The square got rid of the square root, right?
Yes. And good. So let me say here, meromorphic. And let me, because this is actually extremely important for later.
But there is some junk there, right?
Yes, there is everywhere junk, but you put the junk in the right. So let's write some things about this gadget. So this we know we can delete. Whoop. So one thing that is very nice is to try to write your phi 2, how it looks close to these poles also. And please remember this until the end. So, so around t to 0, we will get, where I have this, I have it somewhere. I shouldn't calculate by heart now. No. It's here, sorry. So I get, let me write nicely. That's what I get. As t goes to infinity, this gadget will look like this. So now you are seeing all the things that you know and like. As t goes to 1, oops, here, sorry, here, this goes here, of course. And this is a 3-minute calculation with Mathematica, it's nothing. Or, okay, 10 minutes by hand. So you see, this thing, the only thing it has in life is poles, and this is the physics of these poles. Is this specific linear combinations of masses? Let's really stress that at infinity, you get differences. So at infinity, the puncture is the one that is coming from these d4 branes, and it picks up this distance. And so infinity and 0. So t was going in the backwards way, because I was using this Witten notation. So this is what happens at infinity, this is what happens at 0. At t equal to 1 and q, remember what is this? These are the position of the NS5 branes. So the positions of the NS5 branes, they care about the sum, so the center of mass. Let me write here. center of mass. This is the interpretation. And this goes through in any rank, any crazy quiver, it always happens like this. Good. Okay, maybe very quickly I can tell you how the generalization would look if we would have an SUN. Actually, now I will have these pictures and these formulas. I will just do it on the top of everything. Yes.
So you're saying this is the physics of it, these are the poles and here are the residues at the poles?
Yes, and there is nothing else. That's the important thing. All the physics is in these things.
This fixes the tube form by knowing this data? Totally fixes it? Or
Yes. So, mathematical theorem from previous centuries. If you know for a complex function the fact that it has only poles and you know the poles precisely and it's asymptotics, but now we are on the sphere so there are no asymptotics, you completely fix the sphere, the function. This was the original thing that Seiberg was thinking in his life always, and that's how he started his business. So holomorphic functions fix everything. You wanted to ask something, right?
So this NS5T4 construction has been known for a while.
Yes, yes, yes.
I'm wondering what, because I mean, all of this presumably written you when you wrote the paper about the 40 theory. So I'm wondering what the step was. Well, I mean,
So the amazing step of Gayotto is this.
shift and the square. It's just to identify that as
The shift, the square, and this x equal to Vt. This is also important because this made the t-pole and the 1 over t-pole visible. So these three things, and then bam. It's nothing in some sense, but it's amazing.
And for SUN also, for a higher genus also, you can get rid of the nth root
Yes.
or something like
So let's write very quickly how it should look like, right? So if you had higher genus here, you have to add more lines. So maybe this would be M3, this would be M4, M5, M6. This is what it would be. Here I would have an A1 and an A2, and here one coupling constant. Here I would have to add more. And here I will have to add the 5 and the 6. Here there will be the sum over the 6 guys. This will become a 3. This will become a square. And here I will have a U3 and a U2, or the opposite way. U2 times V and U3. So that's the curve. It's extremely easy. Right? Very nice. So now I want to take this and solve this equation for V. It will have 3 solutions, right? So there will be something like this. And in general, for n, there will be n solutions. So let's write like this, V1 all the way to Vn. So you see now you have an n minus 1 torus that is appearing in this. By the way, this thing, now the modern people, they call it the IR or the M theory or the Seiberg-Witten curve. And this is the Gayotto or the UV curve. By the way, again, your question is, let me write here, 0, infinity, 1, and Q. So your Q here is the position of the brain, of the puncture, is not the tau of the torus. So this whole thing goes through.
So in this case, with the n, it's going to be n root?
Yes, let me write everything. I will write everything for you. So this is what happens in this picture. And then in the Gayotto picture, what happens is that you write like this. X to the n equals sum phi to the L of t, x to the L minus n minus L, sorry. By the way, this starts from 2 because of the Gayotto shift. Precisely, the Gayotto shift is to get rid of the first guy. So this is what you have. And now again, all of these gadgets, the phi to the L.
And guaranteed to be able to write the curve this way? Or it's physics that allows me to do this?
What does it mean that
I mean,
now?
some elliptic curve, some random elliptic curve like that.
It is not very random if you look at it closer. It's not very random.
But this is not, can I not always change the variable so that it will
I don't think I can answer this question because we have to do some more general counting. So, if you wish, the counting that goes in is the following. This is a f of t comma v that has maximum power v to the n, maximum power for t squared. By the way, if I start adding here branes, I can have also t to the third and so on. So this is how it increases. And if you do also the parameter counting that I did for you, you see that you see all of the coefficients of the curve fixed with these parameters and nothing else. And then for this type of curve, you can always do this. So I could, in principle, write to you the most general crazy quiver, linear or elliptic, and you will see that this is immediately always the case. And for linear and for elliptic, I can completely do it by my hand, like always. For more crazy stuff, I don't know if I can always do it. Okay. Good. So now, this is what is going on. But there is one thing. So this changed. But again, here we see that we have a sphere with 4 punctures. But we have to be a little bit more careful for the punctures. So let's say what happens more for the punctures. So for the 1 and for the q, almost nothing happens. It's just that here you have to have the sum. So here you get the sum always. This is a very simple calculation, you get the sum. Here, it's not so simple life. You have to go and check what happens in every single seat. And what happens is the following. You get that there is always a pole, and I can even write it. Okay, let me just write this one. You get m. Let me write actually xi, which is easier, so that I write only linear things. You get, for each seat, so this is 1, 2, 3 to n, mi minus the trace. So, and let's write now another symbol, L left, for these ones. So the sum of these ones. This is m left, and this I will call m right. So here you get this m left divided by t, and here you will get times t. So that's what you get. So these gadgets here, they have n minus 1 parameters. And it was crucial that he did the shift in order to get this minus the trace. So now we interpret these punctures at 0 and at infinity as punctures that have n minus 1 parameters. So they are the Cartans of some SUN symmetry. So this, they have some SUN symmetry. And they call it maximal or full punctures or whatever you want to call it. And these gadgets here, we will keep the dot notation for them. They are parameterized only. Basically, this is the precise U1 that you steal from UN and you put it here. And precisely the shift is doing this job, is making this UN, putting its U1 down here. That's what it does. Is this good? So now we don't have only phi 2. We have phi L and we have phi 2, phi 3 if it's a U3, phi 4 if it's a U4, and so on, and it goes up.
Yeah, so the exercise that you wrote from there, one can compute phi L.
Absolutely, yes.
But how about t equals 1?
T?
You just wrote phi 2.
Yeah, sorry. So this is terrible notation. Let's write like this, x, but this is for all of them now. Let's do this. Yeah, sorry, this is because I used the previous formulas. So if you do phi 2, you will get this type of linear combination squared, right? if you do phi 3, you will get it. So in general, the idea is phi L goes like some mass combination to the L divided by, let's write T minus, it's whatever guy it is, to the L. So that's how it looks. That's extremely important, actually, for me. And for many people, but I will use this, it's very important. Good. And yes, so these positions, again, of the NS5 brains is the center of mass, let's not forget. And this how many things, because there are many brains, we have an SUN. And the U1 went down to the NS5. So that's all the physics. So now let's, okay, good, now we have it. So now we want to make the punchline a little bit. So I delete everything. And I want to very quickly recall what is S duality for n equal to 4, and then try to see what is going on for these SU2 theories.
Can you comment on the singularities in the Coulomb branch?
The what?
The singularities in the Coulomb branch.
I wasn't going to do anything. You want?
Just a few sentences, maybe just for an
What would you like me to?
Pure SU2, we just had 3, right?
So for SU3,
For SU2, it's 4 flavors, the supercon. For pure SU2, we had 1 at infinity and then the monopole point and the dynamic point.
so for SU2 with 4 flavor is the same, but there are extra poles. For SU3, you get 3 cuts, and that makes sense because when you have, so we said that you have to make the thing holomorphic, and the instantons come with something lambda divided by A to the Bn, so then there is a 3 there, so this is why you get 3 cuts. You break your U1 to something that's a discrete group that has a 3, so they have to organize in this way. And as you go up in rank, you have the same type of pattern. But actually, my message, I think, here is that after you learn this Hanani-Witten, you should never go back to the original, because the original derivation is a lot of pain to match all of the monodromies, and this is stupid. This is, everybody can do this. Yes, you didn't understand, because to be honest, I never really explained this. So let me write very quickly. So if you draw, so for just SU2, pure or with flavors, you can draw the moduli space. So you remember was the gauge invariant guy. And here there are 2 cuts. Now, the question is what happens when there is SU3? When there is, and this happened because there is this structure, this symmetry that descends, so you have your U1, but you break it, and the whatever Z4 is left over, it acts on you in this way. Now, if you have, and the way to see this is that you look at the instantons. Okay, there is a coefficient in front that this is the thing we want to find. But here, there is B, and this is the one loop beta function. And for SU2, you end up just getting a 2 here. So this basically is so actually, sorry, you get a 4. Because something like this, I think, is a correct answer. Good, so you end up getting this symmetry. For SU3, you will have, like a Z3 type of thing acting on V. So there will be, of course, U2 and U3 there, and you have to do it carefully. But this is what ends up making you have 3 cuts. So that's what he asked.
I don't think so. I thought, okay, then I have a separate question.
Yes, but this is what you asked, right? Yes, this is what he asked.
I thought you were asking about for higher rank gauge theories. If you're interested in, for example, the singularities of the Coulomb moduli space, which is now U2, U3, U4.
Yes.
Is that something that the Gauss curve gives you access to?
not more than what we knew already.
It gives the complete equal. So it gives the curve. Gives the curve.
Separate from the curve
from
from
there,
the
straight.
So this phi L essentially is UL, right?
It has UL in it, but it's not UL. It also has masses in it. So I can give you, wait, let me, I think I have written it somewhere. No, I didn't write explicitly anywhere. I mean, I can show you later. So it will also have masses in it. And of course it
Where
has
does U
masses.
appear?
Sorry?
Where does U appear?
So when you write the full thing,
Let's see even in this.
yes. So when you write the full thing, it will have some T with some combinations of masses here. Let's write some masses. Plus some U can appear here. Plus some other, and here there will be linear in T. And here there will be again some masses, some combination. And here you have all of this stuff, T minus 1, T minus Q, T. So,
when you have written the previous expressions for phi 2 even,
yes.
M1 minus M2, this kind of thing, for SU2 with 4 flows, there you had suppressed the U dependence.
No. This is an honest calculation. You have to do it, and you get what I said.
So there is no U?
I have to write to remind how you do the calculation, but there is a U there.
No, but not even, I mean, if you know the poles and the residues, everything is fixed.
Okay, very good. This is a very good question. I need to recall this calculation, to be honest. But for that, I will have to write explicitly. There is U, definitely. Maybe not for all else, but for some there is.
And if I'm interested in the singularity of the Coulomb branch, can I just look at this expression and
No. The singularities of the Coulomb branch. I mean, okay, good. Actually, how do you show the fact that there are three? It comes from the fact that there is a v to the third, right? So that's the fastest way to see this. Because what did I draw here? So here I have three things. So this is a 2 torus, and this I can also visualize as a 2 torus. So that's the point.
So I had 3 sheets with 2 cuts each, or
Yes.
2 sheets with 3 cuts.
Yes. Okay, I think everything can go. Good. So, okay, very quickly. So the statement is that n equal to 4 enjoys electromagnetic or duality. And we have this group SL2Z that is generated by a T and an S transformation. T sends T to T plus 1, and S sends this to this with a minus. So there is this symmetry. So this means that if you have an n equal to 4, so a theory with some color group G and some Campli constant tau, what you get is that there is this Langlands dual group with this, and these two theories are supposed to be equal. That's the statement. And this was from what it was, 77, I think, Montonen and Olive. And yeah, I don't know, Sen wrote this amazing paper. I mean, anyway, everybody believes this. And the point is that, so then Vafa came later, in I think 97, and he said how to understand this from 6 dimensions. And it was a very simple, stupid observation that you can take the 6D 2,0 on a torus. You can also do the stupid dimensional reduction and get n equal to 4 if you want. And precisely the modulus of the torus is the tau of n equal to 4 super Young-Mills. So this was the status of affairs before Gaiotto came into business. And maybe another thing to say that is nice is that by now we can understand, so in Triligator, together with Cordova and Dumitrescu, they wrote this very nice representation theory paper a couple of years ago, and they studied all possible 6D 2,0 and 1,0 short multiplets, and basically there is no way to have a marginal coupling in 6D 2,0 or 1,0. So this says that whatever coupling you will get in 4 dimensions by doing this business, you can only get it from the moduli of the whatever surface you are putting your theory on. So for n equal to 4 super Young-Mills, there is just a tau, and that's the one of the torus. And the same thing will happen if I put my theory in a crazy surface. I will get the whatever moduli the surface has. So this theorem is sort of important. Maybe I write. From representation theory alone. Good. So now we go to Gaiotto. And we will get what is class S. And I am discovering now class S with the curves, but you can do it also with the index, or with your instanton partition function, or with your favorite object. So Gaiotto said the obvious. Let's do the same thing here. We can get a large class of n equal to 2, and we label them theory G, comma n. So this is the genus of the surface, and this is the number of punctures. On some Riemann surface with genus G and n punctures. So that's the point. And again, like also in here, so 6D 2,0 comes with ADE classification. So this gives you a way to get all possible groups that you like in 4 dimensions. Okay, not all possible, ADE at least. And when you make this statement, there is another thing that you have to start thinking. So when you have these Riemann surfaces, you can start decomposing them, right? So a Riemann surface can be decomposed to pans and cubes. So let's really explicitly see this now from the curve, to start believing that we are understanding everything. This is done. So let's take the curve we wrote before. So let's do this example. And let's take the weak coupling unit. So what happens? So this was the one puncture that is at 0. Let's also call names. A, B is the puncture that was at Q to make it more visible. So, okay, this is of course just drawing, but this comes together, and these points are far away from this now. Before we had a very explicit formula for what this guy is, and it was some type of polynomial divided by so this was like this. And I did this yesterday. I put this in Mathematica, and what you get is the following. You get the following. Let me write it here so that it's a little bit nicely. So you get and I will immediately tell you what these things are. This is what you get. And where m infinity is okay, in this notation that I'm using, this is actually A now. So this is a simple calculation. This was from for the 4 puncture sphere, and this is from the 3 punctures now. So I started with something that has 4 punctures, and I ended up with something that has 3. And this is basically this part. So now when I took this limit, I lost this part of the curve, and I stayed with this one. And also look at this object that is corresponding to this thing. It came from the Coulomb moduli, which becomes now engaged. And if you wish, this precise structure, of course you can immediately interpret it as a sphere with 3 punctures. But you can also derive it for yourself the way we showed before, if you start with this structure. So this will be the m infinity. This will be this A that I have, and this. Okay. This is what you have. So you can derive it. So there are 2 independent ways to get the same thing. And you can continue playing this game, because as duality is supposed to be that there is another theory at the strong coupling, right? In fact, there are 3 channels that one can study. So you can do this channel. We can write here a Q, because this is the guy that we make weakly coupled. We can study, let's write explicitly. Q going to infinity. By the way, note that U going to infinity is basically the same as this, because you can think of it as exchanging the NS5 branes. So it doesn't do anything to our diagram, so it's clear that it's going to give. And this is another weak coupling type of limit. So here you will have the infinity, which was D, Q because it goes to infinity, which was B, 0, which was A, and 1 will be here, which was C. So this is how you should draw this. And what you do when you take this limit is that you lose this part of the curve. You lose it. And you end up with this part of the curve. And you can again explicitly go to your Mathematica file, put q to infinity, and you will get precisely this. It's just that this formula that I have here, it will be with M3 and M4. And maybe a minus here or something. Good. And then there is the third way, which would be to send q to 1. If I do this, I have B was Q, C was 1, A and D is 0 and infinity. So when you take this limit, you lose this part, and you end up with this thing. And here what you end up getting is you end up getting M1 minus M2 for this object, M3 minus M4 for this one, and for here a more complicated linear combination that you interpret as the other one. So you see that all of these three ways to take these different limits of Q, this is precisely the statement of Gayotto. Decompose the sphere in three spheres, and the tube is a gauging. So everything is made out of these objects that will be, Gayotto calls them free trinions, and tubes, that is the gauging. And you can put a Q on it if you want. And here there are specific linear combinations of the masses that you have to calculate.
In the case of this three-punctured sphere, when you do this de-aberration, there the masses for this other guy would be Coulomb branch.
The mass is what?
Masses of this.
Yes, the Coulomb branch is always there in one sneaky way. So in this type of calculation, it comes out very easily. When you do the weak coupling, here it comes in a more ugly way, but it comes, yes. And of course, now this statement generalizes immediately when we do SUN, for example. So let me just, on this picture, do it. So on this picture, remember before we had that the 0 and the infinity, they had this SUN type of puncture.
So what is the statement of duality now?
The statement of duality is that it's a self, SU2 is a self-dual guy, basically, because it always breaks to weakly coupled SU2s. So all,
Permutations of masses.
yes,
So
with
is
with
that the mass
relabeling,
of the-
yes, yes. So let's write it,
So
very
without
good.
the degeneration also one can just take this and say, see that a simultaneous action on the masses is permutation and the action on the tau would keep the curve invariant.
Yes,
That's
the form of the curve. And in fact, you can do another thing. I started doing yesterday but I got bored. You can in fact see the symmetry enhancement if you want. So in some sense, you see the symmetry enhancement is almost immediately in this Hanani with. Okay, so this is, I don't know if you don't understand. This is 3 seconds. So one other way to rewrite the curve
in terms of mass.
is this. So there is this Hanani-Witten phenomenon that you have your D4 brain and you go through an S5, and these end up being these 6 brains. And here you have 4. So here, even if you are stupid, you see an SU4. And then with a tiny little bit more care, you see the SO8. But okay, this is really for if you know what we are talking about.
But at the level of the curve, one can just see the
You can at the level of the curve, you can always see the symmetry enhancement by organizing your parameters in nice ways. And also there is some rewritings you need to do that mimic this Hanani-Witten move.
So in the curve there is U also, right? They used to do with 4
Yes. So you need to put it somewhere. You need to use it.
So U also needs to shift. So
You need to, yes, you need to organize things in a nice way. I can show you explicit calculations I have in a paper, but straight I cannot just reproduce.
Like how does the duality act on you?
How the duality acts on you. Okay, you have to be careful. Yes, yes.
Some symmetry of the curve and
Good.
computations are-
So when you do this type of calculation, for example, already for the weak-to-weak coupling, here you will not get the A straight precisely like this. You might get it with some extra masses. So there is a shift. And in the case where you do the strong coupling, the relationship that we get is more complicated. So yeah, this precisely is how the thing acts. But you really need to write explicitly to see this. I didn't write explicitly enough to see this.
Simple way that I set all the u's to 0 and then the curve has to be symmetric.
If you set all the u's to 0, if you set all the u's to 0, you will not see the symmetry, right? Because you see only one. Wait, which u's? Which u's? Wait. No, the u's. Yes, the u's, you don't want to set them to 0, right? Because if you set them to 0, you will lose this puncture.
No, I'm not doing degeneration. I'm not doing degeneration. I have a curve, Gaussian curve for SU2 with 4 flavors, and I want to see the duality. Okay. Now the curve depends on the bunch of masses, 4 masses.
Okay, so I haven't done this exercise. We can do it.
And
Yes. So you want to see the symmetry enhancement straight.
Not enhancement. I mean even just the duality, right? Let's say. So I was thinking of seeing the duality should manifest itself as some permutations of m's along with.
Yes, this is maybe
a change in
fast.
tau.
This is maybe fast. I have not worked it out, so I don't want to say.
Okay.
Yes. I think this is the best way to see the duality, the way I did now. So you always realize that there is a Q. So this Q is the original Q. This you can say that there is a Q prime that is 1 over Q. And here you can say that there is a Q prime or double prime that is 1 minus Q. So this is the redefinition of the Q. And the relabeling of the masses, I almost said it. So this is the one way. The other way you put M3, M4. Okay, here is a little bit more complicated, but with this you have the precise same curve.
So is there some like T goes to 1 over T type thing for SQLT?
Sorry, a what?
So like the way Abhijit's saying is you want to think about SQLT as like a map under which the curve goes into itself.
Yes.
So then would you have to like change the T's as well? I mean,
The
your-
D's.
No, the X and T are the variables of the curve, right? X squared.
No. So for this thing, you don't need to change the variables. Okay, maybe T goes to 1 over T, but that's stupid. You don't need to. I mean, this is a very minimal change. So clearly here, I delete. No, I delete this part. Whereas here I delete this part. So here there is clearly a symmetry from T going to 1 over T, but that's a very minimal one. But to really see what you want, you have to do a little bit of work. So it should be possible, but
Presumably it holds only at the origin of the Coulomb branch, right? What does it mean for this duality in the Coulomb branch?
Yes, no, it should be at the origin, I agree. Okay, one more little thing, because basically now we have it. Yes, the SUN case, I started doing it. So this is what you would have here, this is what you would have here, and now this is what happens. You get some new object. Okay, let's write slower. So, from this type of picture, we see that there is this type of object with 2 SUN punctures and 1 U1. And this is the free trinion. So the free trinion is an n by n free hypermultiplet. So this is the curve for that, and you can also derive it by having here 1 to n, 1 to n. So this is the same thing. Now, here there is something different that is coming out, because this, it will give you also n-1 parameters from all the A's and all the other masses that you had. And here you get this type of object, which is now, this is the new thing Gayotto did, right? Okay, if you do this exercise for SU3, and that I have done once in my life, and it's nice, you discover that you get a curve that has this 6 symmetry, and this was precisely this Argyre-Seiberg theory. But then, okay, Gayotto told us that there is this thing for basically higher, but of course, one thing, in order to discover this for higher n, you don't do this decomposition, you need to do something a little bit more advanced. You need to do the following. Or maybe let me write the quiver. You need to start with a quiver with n nodes. And then if you take the strong coupling limit, you get this theory.
What happens if you just do this for SVN with 12 nodes?
You will get some more, a little bit different. The one puncture will be a little bit different. Good. Here I can say something else also. In the class S, and this is almost immediate in this language, there is this classification of all the different possible punctures. And in fact, here with the curves, it's very, very easy to see. So we see that a curve has masses that parameterize here the position of these branes. So if all the masses, you allow them to be different, so all of the positions of these branes are different, you get what is called the full puncture, which is this. And this is labeled by some Young tableau. This is just notation that you have n guys all straight. But then you can start doing the following thing. You can start making, let's say, 2 of them to become equal. So 1 and 2 coincides. When you do this, so let's say M1 equal to M2. What you are instructed to do is you are instructed to put 1 down, and here this is n minus 1 in this direction. And you can go all the way down to this, where you put everything to be equal up to only 1, and this is equivalent to this U1. So this is the complete classification of all the punctures that you are allowed to put in class S. And this is extremely easy in this language to see. Okay, good. Yes.
You're saying, Eli, that you just take the Seiberg-Witten curve, let's say let's say
Something with SUN.
So sphere with 4 maximal punctures.
Yes.
It has a bunch of masses.
Yes.
You take that curve, and now you just set a bunch of masses to be the same.
You
and
start
get the curve-
imposing, yes.
You get the curve of the SUN with 2 enclaves.
Yes, with lower.
Smaller punctures, and then.
And in fact, this calculation, it's not only, you can also do it actually at the level of the partition functions, and there is even more impressive. Actually, it's extremely impressive, because there you have to do also integrals, and there is a phenomenon where the integrals get pinched. So this I have done explicitly, and it's really a magic. It's a very hard calculation, but you can really see how it works, and you really see this thing happening in front of you, very non-trivially. So it wants to happen. It's the truth. Okay, good. And then one last thing. So because you see, here we have everything, right? So because I would like to have AGT. Okay, and I can clearly not really explain now AGT, but we almost see it if we are smart. So statement number 1, and you can complain, but it's here. This is really like the bootstrap, right? This is really like the crossing symmetry, and you decompose. If you wish, you can do something really terrible. You can say, let's label this by some diagram like this with A, B, C. Then you can write that this thing is some A, B, C. Let me put the Q here to remember how the weak coupling happened. So this is the 1 over Q. A, C, B, D, and here this case is the B, sorry, CB, 1 minus Q, AD. So if you really make these identifications, this really looks like the bootstrap, like the crossing equation. And by the way, already, I don't know, Bilal, for example, if you read the Cyberwitten of Bilal review, he says in the conclusion that it has to be that there is a 2D CFT. So already people were dreaming about that.
Yeah, so
But now we see very concretely how these things should actually work. So in fact, we can really start making a dictionary.
I have a question.
Yes, please.
So this HGT is a correspondence for the sphere partition function, right?
Yes, yes, yes.
Or whatever.
But the important thing is that it's a manifestation. So the sphere partition function is, so in some sense everything is Gayotto, and AGT is a manifestation of Gayotto.
So what I mean is, why is it even, why is the correspondence true only for these observables, even for some other observables?
For all observables, the correspondence should be
How
true.
about the thermal partition function, non-supersymmetric thermal partition?
Because we don't know how to write it down.
But
If you
saying
could,
it should be true there.
okay, I don't know what
Thermal
happens.
partition
Okay,
function,
good.
non-supersymmetric
I
thermal
don't know
partition
what
function of
happens
that
when you
series.
turn on temperature to these things.
But it's manifested as you were saying.
No, okay, good, good. I don't know
So
what
where is
happens.
this state?
So I don't know. So the statement should be the following. Any possible observable without doing terrible things in life, and terrible things means breaking supersymmetry, okay? So any observable of the theory itself, so let's calculate an anomalous dimension, for example, right, of an operator. There should be some type of Gayotto or AGT or whatever you want to call it also there. But we just don't know how to do it. If you break things, that is yet another madness.
You are
Yes.
breaking the supersymmetry, you are looking at non-protected operators. All this
The fact that you look at non-protected operators, it doesn't mean that you break supersymmetry. As you know very well, in the integrability business, in order to compute anomalous dimensions, there is a way to fix everything by symmetry, basically, for n equal to 4. So you use the fact that there is a PSU2,2/4 guy. If you break this, hell breaks loose. So I want to say that I truly believe that if you don't break supersymmetry and you have your full supergroup and everything, life should be good to you, and you should have this type of duality for different observables, even non-supersymmetric. But then good luck.
The only way it can fail is that the S duality somehow does not hold when I put things on.
Finite temperature, for example, yes.
Finite
I don't know what happens to S-duality then. But then we have to first ask what happens to S-duality
But
when I
is-
do n equal to 4 super Young
So
Mills.
S-duality is a statement that, let's say you have some spectrum of the theory at tau, at coupling tau, and the spectrum of theory at coupling minus 1 over tau.
Yes.
Is the spectrum identical, or only the spectrum of supersymmetric states is identical?
So the only
If it is
thing,
the former,
good,
then the
good, good, good.
competition automatically.
Fantastic. So, fantastic. So, the only things we know in life is the spectrum of BPS gadgets and the index, and nothing else. Now, there was also a little bit this paper of Leonardo with Chris, and where they started doing something with Conissi or some, but I think this is completely preliminary. So I would say that I would believe, and it would be amazing to try to find a way to check it, that you can find, let's say, Conissi in the two theories and compare. And it should be self-dual.
Yes.
That I believe.
Okay. So then thermal partition function.
Thermal is very bad because temperature is really crazy.
No, but just the the spectrum is the same. Then you can go to
No,
the
but
thermal
operators maybe will acquire extra anomalous dimension because of the temperature dependence. So this part, I don't know what to do with this part.
No, I just mean, you just sum over the operator spectrum with some
If you
trace
just,
over the operators with
so
equal
good,
minus
so
beta
thermal
edge.
partition function, then
That's
you
it.
don't mean it that you turn on temperature really, you sum over all possible states, that's what you mean.
With e to the minus beta edge.
So I don't know if I like the beta.
No, that's
So
just
my
a counting
problem,
parameter, right?
yes, I know.
In some sense.
So if somehow you have a way to just count the operators, I believe that they have to be equal. But temperature also breaks supersymmetry. Yeah, okay, yeah. So, for example, people have calculated this one loop partition function. So there is a tree level that you can write down and the one loop. For the one loop, there should be a way to do something there.
Yeah, well, loops are not strong.
They are not so good. Yes, they are not good.
Want some exact non-supersymmetric thing, which is
Okay, first of all, okay, this is maybe a comment. I want to just make a comment, and I wouldn't say it, but maybe I should just. So, first of all, for the people that they really know to DCFT, it's not insane when I give you a curve to start thinking that there is a connection. Why? So, people in 2DCFT, one of the ways they compute is with this Coulomb gas approximation. And if you write that, you get some type of matrix model. And always when you have a matrix model, if you take the thermodynamic limit, you always get a curve. And let me also put it, yeah, I mean, yeah, I think. So it's not insane, this statement. So now let's do something better, because we have not just a curve, which is maybe written in a terrible way, like the old school that Seiberg was writing and Witten. Now we have this Gayotto curve that is amazing. What this Gayotto curve did, so when we looked close to the poles, remember for this Z2, we got something like this. Wherever the pole is, some linear combination of masses and some double pole. And we also wrote this type of equation for higher. So again, there will be some type of linear combination. So this is this is really schematic now. Okay, so this is what you get. Now, if you have ever taken one class on CFT or whatever read by yourself, the first thing you ever learn is word identities. Let's write the word identity. So the word identity is this. And you see already I started writing Z and ZIs because I want to make things look the way I want them. So that's the word identity. So if you have ever seen this thing in your life, and you see this, because you know, we know that there is we know that there has to be some relation, right? And let me also write another word identity here to make it even more, because I make it look like it's magic, but maybe if I write also this, you get some gadgets that are the higher spin. Okay, plus whatever descendants on the same stuff. So you see here, this is this power, this V to the L. So if you have seen this in your life, you already know what is going on. You know that you have to identify this object with this precise linear combination and this object with this precise linear combination. If you do this identification, you have almost the full AGT dictionary together with this, of course, up to the epsilons of Nekrasov. Everything else is here.
We don't even have to look at the partition functions
Yes,
at this stage.
yes. So let's write.
But what is the intuition behind comparing that to this, apart from looking at these power subsets?
The intuition, I think, is always if you have a function and it has poles, it's being fixed. I think it's this stupid thing.
We are looking at when you are doing that OP, you are taking T of Z and you are moving around and you are encountering V and you see the matrix. Similarly, you take phi to Z, one, wherever there is a function, you see this diagram.
So from the point
The
of view
function is a V.
Right. So from point of view of the CFT, we have this phi is just an auxiliary function which encodes the vertex operator.
So let me make a further statement. Let me make a further
How
statement.
about the next term, del bar, del I?
So here there is the maximum W, the whatever minus 1. Sorry, this is the 0. And here you have minus 1, minus 2. So you start going in the multiplet.
No, even the T, derivative.
The derivative is the L minus 1.
Yeah,
But in the 4D.
So this has to act here. And it will bring down things.
No, but from the curve, do I see something like that already?
Good. No. So I will tell you immediately. So this was close to the poles. So now let's do the full calculation. Let's do this calculation. T of Z with V1, V2, V3. And let's just do as U2 because we are stupid and that's the only thing we can do. And let's divide by this. And in fact, let's be the most lazy idiots in the universe and let's not even do real thing. Let's just take free fields. So let's just take V equal to E to the alpha phi. And let's just do wing contractions. If you do this calculation, you get this. With this identification that I just said, you get precisely this. This is an equality. You get everything. By the way, let me put a 3 here. First of all, because this is my notation. Also to remind us that this is the free trinion. So this is for this. You get precisely this. And if you do also the same calculation, and again, the best way is to be stupid and do it with weak contractions. And let's also take that this one is simple and these are full, and the same here.
This weak contraction, stupid thing that you are saying is essentially Coulomb's formula.
Yes. You get this. Bam. So that's actually insane. Now, what is going on here? Okay, at the level of Virasoro, this is almost trivial, but when you really generalize also to any n, by making this identification of masses with with conformal dimensions and of these things with the higher spin charges, you actually really, because if you give me all the higher spins and the conformal dimension, you fix what is the representation of the W algebra. So basically, by doing this identification, what I have done in my life is that I have fixed the representation of the W algebra that I'm looking at. So this is fixing
Yeah, there is no more information.
there is no more information. That's fantastic, because this allows me, first of all, the moment I know the representation, I can write down conformal blocks. And I can write down explicitly as much as I like.
But you
And
don't know the algebra, right?
W algebra.
Well, you don't know the central charge.
No, good. Good, very good. What you know is that it starts with n. So this will be inside the calculation. So you get the answer for q is equal to 0, or better if you wish epsilon 1 and epsilon 2 is equal to 0. That's the answer you get when you do this.
Okay.
But you know that this has to be some W algebra with some central charge that you don't know. That's, yes, for sure. So you write down.
This limit is large C limit or what?
No, that's n. So the C starts with n. And then there are, or maybe n minus 1, and then there are corrections that are proportional to.
So it's C of the
It's 1 plus 6 square.
Good. So good. So for Virasoro is this very good.
No, doesn't it depend on epsilon?
This is epsilon.
Yeah, that's what
Q
I'm
is
saying.
equal to epsilon 1 plus epsilon 2 divided by epsilon 1 epsilon 2 square root. So in this limit, I mean, effectively you can say you don't have this.
Z plus 1. Okay.
And for Toda, you get n minus 1. So you are not stupid. You start seeing what is happening. And in fact, also here, so the precise coefficients inside this curve, they know all about all the null vectors because of these dots that I didn't put. So they really know everything. So you can write down a block if you know this. And by really, because then, okay, for 3-point function, this is easy. But then when you start going to 4, it's bad. And you don't know, also, the 2D CFT people, they don't know how to do it
So
exactly, right?
this is what I want. So you're saying you can write down the block, but for the block I need to know the central charge. Here you're just telling me.
You put a C, very good, put C. Leave it as an unknown parameter,
Right.
okay? So
How
just,
will I fix C?
you will not fix it,
Okay.
okay? Just put C and calculate it.
Okay.
So what you will get, you will get something that looks like Nekrasov partition function because you have to start. So this is stupid 3-point functions. Now you want to write the big block. You want to write this with a Q here. Okay?
Yes.
So you start writing. The moment you start writing,
Then this is a block of which representation in the middle?
so good. So let's do Liouville because let's do Virasoro because we are stupid. You put a generic representation here in the middle. So you put all generic representations, and you start writing it down. You will start seeing that it really starts looking like whatever you have here for instantons, one by one.
Yeah, so the external guy's information will go there.
Yes,
The
and in
internal
fact,
guy-
the central charge in this Virasoro case, it appears in the 2 instanton, I think, if I remember correctly. So already you can make one check without caring about the central
No, but
charge.
what is the internal guy? What is that?
It's some representation, some, you
No,
don't,
but on the right hand side, it's a partition function. So there is
wait, there is no partition function yet. So this is a block, okay, and you just write it out, and it is what it is, bam. Now you look at it,
Okay.
and you start recognizing the pattern.
Okay.
And you see Nekrasov, basically. You just see with your eyes. You see 1 instanton, 2 instantons, because of the precise way. So if you have played a lot with Nekrasov also, you know how in the denominators the masses should precisely go, how the A's should precisely go.
So, how much
The
information?
age, what primary is strength?
So in Virasoro, nothing. Just pick the general representation with no null vectors. Just pick the most general. When you will want to do the Wn, if you don't want to completely die, you should put 2 and 2 simple, if you don't want to die. I don't know if you are stronger than I cannot. But you can definitely start writing an expansion.
There's one thing
Yes.
the precise thing which fixes those operators, external operators, are the Coulomb parameters here. They have a middle there.
Yes.
Very cool.
So that's what's going on. So the statement is, starting by this stupidity and these observations, you can almost rediscover AGD. There is one thing left, which is the 3-point function. That's the only thing that you don't know. Because to specify a CFT, you need to give me what is the central charge. Sorry, the 3-point function. So either you take this block and you try to solve the bootstrap, and then you are called Zamologikov or Testner or someone super cool, or you are very lucky that Zamologikov wrote down the answer, right? You look at what Pestun wrote, and it's the same. And this is what happened to them. They were very lucky.
Presumably there are other solutions to the bootstrap also.
Very good. The answer is if B is real, no. If B is complex, absolutely yes. And there you have to be again. Anyway, yeah.
B being on the imaginary thing was the kind like
Yes, precisely.
Which was?
Atish was talking about.
Yes. So there is a solution of the. Good. Let's write. Let's write. So the DOZZ is a formula that up to constants that I'm not going to write because I'm super lazy.
This is like a unique solution to the
Yes,
equation.
if B is real.
Sorry, can you remind me what B was again?
B, yes.
So there is what? So there is
Okay.
only one CFT with
Yes.
put B equals 1, okay?
Yes. So, okay, there are two requirements, and then it's unique. So, this is one requirement that B is real, and the second requirement is that for every operator of some conformal dimension, there is no second one. So, actually, that's the one that does the job. So, Liouville is the theory. Is this theory? Okay, now I don't need my notes because anyway nothing is in there. And if you write the guy with the file reflection, so because if you write V Q minus alpha, right, this object has the same delta. But then you impose that there is a relation between them, and that's called the reflection coefficient. So this is only one, basically. You take it as one vertex operator, not two, one. So no degeneracy plus this is real, this is a unique solution. The moment you say, for example, that B is imaginary,
Also for dimensions of some specific, some
A is, if you write this as Q divided by 2, I don't remember now, plus or minus IP,
I, right?
for any P real,
Yes.
it fixes everything.
Right, but you know, if you forget this for a bit. and just
Yeah,
talk about
yeah,
two
very
CFTs,
good, yes,
two
yes.
CFTs. So yeah, let's take B equals 1, okay, that's real. So that's what, 13, C equals 13,
Yes, yes,
right?
yes.
So that's
No,
the
it
form
is
between C
important.
equals
It
13,
is
right?
important where you integrate.
So in general,
Yes,
my dimensions,
Yes.
as a normal person, I would look at dimensions which are real and so on, right? What?
C was 25.
yes,
Square, yes, 25.
Yes.
So I would look at dimensions which are
Yes.
positive and positive real,
Hmm.
not this crazy 2Q over 2 plus I. There is a motivation to look at that also.
Yes.
That's probably related to this
Yes.
principal series or something.
Yes.
Right. So, but if I do that, then there are many solutions.
Yes, yes,
Right?
absolutely.
Many CFTs.
But here I also fix
But
the
is that
contour.
is this a statement that if the theory is living on the principal series, then there is a unique solution? That's the point. Yeah.
For
This is unique.
yeah. For bootstrap, if you consider only the principal series guys in the middle, and then this is
Oh wow. So can I make an off very unrelated comment now?
Yes.
So I looked at bootstrap equations, the system of bootstrap equations, precisely with principal series representation, the higher dimensions.
Mm-hmm.
I found a solution which is precisely generalization of the DOZZ.
Mm-hmm.
And now I suspect that it's unique.
Mm.
Okay.
Okay, that's it, I think. If you like all of these things, I am very ready to go to the next, to the SK. Should we stop or?